because this is such a huge topic and we're only going to kind of barely breach the surface of it, we're going to start off real slow. And I like to think of this as kind of the way you started off with algebra in general. You didn't just jump into solving systems of equations when you were introduced to algebra. No, in like third or fourth grade, you're first introduced to what a variable is. And the way you're often introduced is by first learning to check whether a value is a solution to an algebraic equation. So you might be given like x plus 4 equals 7. And then your teacher would be like, check which one of these is the solution. X equals 2, 5, or 3. And so what you start off doing to check is just plugging those values in one by one, and you'd go, all right, 2 plus 4 equals 7. No, that doesn't work. 5 plus 4 equals 7. No. And then you go 3 plus 4 equals 7. All right, that works. And we're going to do the same thing today. I'm going to introduce you into the concept of a differential equation and tell you what their solutions look like, and then we're going to check solutions to differential equations. So you're not going to be solving them. I'll be giving you the solution, and then you'll be verifying that it is a solution by plugging it in and showing me that both sides come out equal. Before we do that, you need to know what a differential equation is. So lots of things involve an unknown function and its rate of change. For example, population growth. If you think about general population growth, and we're just going to not add in all these other variables like environment size or food source or predator versus prey systems, which you will cover in Calc 2 if you take that. But so just unlimited growth, like bacteria in a petri dish that you're feeding, right? It's a reasonable assumption that the population growth rate depends on the size of the population, meaning at first when the population is small, it grows slowly. But as the population grows, then there are more bacteria to replicate themselves. So it begins to grow very quickly, right? So when I say the population growth rate is proportional to the size of the population, I'm saying, okay, there's some unknown function. Let's call it the population function at time t. I don't know what the equation for that function is, but it exists. And I know that it's reasonable to assume that the growth rate is going to be proportional to the size of the population. Well, proportional to just means equal to times a constant, right? So if I say the growth rate, well, a growth rate is a rate of change, which is a what in calculus? Derivative, a slope, right? A derivative. So the population growth rate would then be dp dt, right? The derivative of population at time t. Is proportional to, meaning equal to times a constant, the population itself. All right, so this is going to be our definition of a differential equation. It's an equation that involves an unknown function and at least one of its derivatives. Oh, let me write that out for you because apparently I didn't define it. These are sometimes referred to as diff-EQs. So differential equation is an unknown an equation involving an unknown function and at least one of its derivatives. Okay. The solution, let's actually do this first. The order of the differential equation is the highest number derivative. So it's kind of like when you identify the degree of a polynomial, it's the highest power on your variable, right? So like a quadratic is a second degree polynomial. A cubic is a third degree polynomial. The order of the differential equation is the highest order of the derivative. So if it only involves the first derivative, like this one, this is called a first order diff-EQ. If it were an equation that also involved the second derivative, it would be a second order differential equation. Does that make sense? So it's just a way to classify the differential equation. All right, the solution to a differential equation is solving for the unknown function. So in an algebraic equation, your solution is a value for your variable, right? Or for multiple variables, whatever it is. In a differential equation, the solution is a function. You're trying to figure out the unknown function. Sometimes it'll be a family of functions. All right. Oops. Sorry, I didn't realize I was off screen. There we go. All right. So let's see what I mean here. I'm just going to skip to this example. So here it just says, show that every member of the family of functions here is a solution to this differential equation. All right, so this is a differential equation because it involves an unknown function, y, and at least one of its derivatives, y prime. So when I solve that differential equation, I would try and solve for y. As I told you, today we're not going to be solving, we're going to be verifying solutions, okay? So I'm telling you that this is the solution. Here is your unknown function, and I want you to prove to me that that's true. We're going to do it very much the same way I did with the algebraic equation on the first page, right? I just plugged it in, and I show that I came out with what's called a tautology, where two sides are the same thing. They're equal, right? And that's what I want to do here. So I'm going to take my function y, I'm going to replace y in the equation here, and then I also need to find y prime, and I'm going to replace it here, and then I need to simplify algebraically until it's clear that both sides are truly equal to each other, okay? All right. The first thing let's do is find y prime. Well, y prime equals. In this case, c is a constant. So we're going to treat c as a constant. All right, so back to derivatives. What rule am I going to have to use to differentiate this? Quotient. All right, let's do this. So I'm going to do this in a couple steps. It's been a while since we've been taking derivatives, but I'll do low, which is 1 minus c e to the t, d high, so I'm going to do d dt of 1 plus c e to the t. I'm not going to do it right now. I'll do it in the next step. Low d high minus high, 1 plus c e to the t, d low, so times the derivative d dt of 1 minus c e to the t, over the denominator squared, right? 1 minus c e to the t quantity squared. Okay. So now let's focus on the calculus. This part, what's the derivative of 1 plus c e to the t? Well, the derivative of 1 is 0. What would the derivative of c e to the t be? It's just c e to the t. right? All right, so here I just get CE to the T. Then I have minus 1 plus CE to the T. And then the derivative of 1 minus CE to the T would be negative CE to the T. And that's all over 1 minus CE to the T squared. That's y prime. I'm gonna simplify that a little bit, just because it's a little messy right now. And so here's how I'm gonna actually, I'll plug it in and then we'll simplify it. So this is my expression for y prime. So what I'm trying to do is verify that this is a solution to the differential equation. So what I want to do is plug that in for y in my differential equation. That's going here. Then I want to plug this expression in for y prime. So that's going on the left-hand side. And then I just want to simplify using algebra until I do get clearly both sides are the same. Yeah. Where is the original y prime? Because we're verifying that this is a solution. So we can't have y's in there, basically, because y is our unknown function. Yes, but then you're not proving that this is a solution. So when you say use the original y prime, you're saying plug this in for the left-hand side, right? You're kind of creating a tautology on its own then, because you're not it equals itself, right? You're not verifying the solution. All right, so let's do that. So here's what I'm going to get. Y prime on the left is now this big mess. 1 minus CE to the T times CE to the T minus 1 plus CE to the T times negative CE to the T all over 1 minus CE to the T quantity squared. And now that's equal to the right-hand side, which is 1/2 times the quantity. Now we have y squared, but instead of y, we're going to plug in what they claim as the solution. So it's going to be 1 plus CE to the T over 1 minus CE to the T. And then I'm going to do quantity squared plus 1. All right. All right, so it's not immediately clear that these two things are actually equal. So we need to work algebraically until it's abundantly clear that they're the same things on both sides. Now this is kind of messy, but here's what I would probably, there's a ton of ways you can start this out. But I would say, I notice here and here, I have a common factor of CE to the T, right? So I'm going to factor that out. So I'm going to pull CE to the T out front. But notice that this one has a negative. So it's going to make this positive, right? All right. So if I pull CE to the T out front, here's what we end up with. So I have CE to the T times the quantity 1 minus CE to the T. Whoops. Plus 1 plus CE to the T. All right, and that's all over 1 minus CE to the T quantity squared. All right, I'm going to leave the right-hand side alone for right now. I'll come back to that in a moment. So I'm just going to continue to simplify this. Well, I can get rid of these parentheses because now I just have basically an addition problem. And notice what will happen is I have a negative c e to the t and a positive c e to the t. Those cancel. And I'm just left with a 2 in the numerator, or a 2 c e to the t, I should say. All right, so I end up with 2 c e to the t over 1 minus c e to the t quantity squared. All right, so that's what I got the left-hand side to simplify to. Now my right-hand side, this equals 1/2 times 1 plus c e to the t over 1 minus c e to the t quantity squared plus 1. Oops. All right. So what do you guys think? Where do you want to go from here? Oh, -1? Did I write that wrong? -1. I don't know. Because I misread it. Sorry. All right. But we're trying to show that these are equal. Well, one thing I could do is just multiply both sides by 2 to get rid of the 1/2 in front, right? So if I multiply both sides by 2, I end up with 4 c e to the t over 1 minus c e to the t quantity squared equals, so that's what I did there. And then I can just view, I can square both the numerator and denominator, so I have 1 plus c e to the t squared over 1 minus c e to the t squared. And that's -1. So we're getting closer because look, now we have matching denominators here, right? So that's good news. So the next thing I would do is probably expand this numerator, meaning multiply it by itself, right? And when we do that, I'm just going to work on the right-hand side now because I'm not going to mess with the left anymore. I'm just going to try and get this whole side to come out equal to the left-hand side. So if I multiply it by itself, if I use FOIL, I'm going to go 1 plus 2 c e to the t plus c squared e to the 2t. That's what that would multiply out to. And I'm going to keep the denominator as is, so that would be 1 minus c e to the t quantity squared. And now I have -1. All right, well, I can incorporate that 1 into the fraction by making it, instead of 1, I'll just rewrite it as the denominator over itself. So it's 1 minus c e to the t squared over 1 minus c e to the t squared, right? That's the same thing as 1. I know this is tedious, but you're following? Trust me, this is tedious for me too. I just want to get to the point where they are equal. So the last thing we're going to do is multiply this one out by itself. And so that's going to multiply out to almost the exact same thing as this one, except since this is minus and this one is plus, the middle term is going to be negative instead of positive, right? So that's going to be, 1 minus 2 c e to the t plus c squared e to the 2t. Okay. So the last thing to remember is that we are subtracting that whole thing, right? So this whole thing is getting subtracted. So look what's going to happen. I know I'm doing this a little bit sloppy, but I'm taking that I put in red parentheses, I'm subtracting what I have up there in blue parentheses. So what's going to cancel? Ones, those are gone. Now the 2c e to the t minus negative 2c e to the t, that becomes plus, right? So it's 4, which was what we wanted, 4c e to the t. And then this c squared e to the 2t, those cancel as well. And I end up with 4c e to the t over 1 minus c e to the t quantity squared on both sides, here and here, and I'm done. I've now verified it as a solution to the differential equation. All right, not all of the verifications are going to be that long or tedious, but they all involve the same idea, which is essentially exactly what we do algebraically again. In algebra, to verify an equation, I plug in a value for x and I show that both sides are equal. In calculus, to verify a differential equation, I plug in a function for y and its derivative for y prime, and then I show, once again, both sides are equal. All right, but look, this solution is a family of functions because it has this constant c, and c could be any value, right? So oftentimes we're interested in a single solution, not a full family of solutions. So to have a single solution, what we need is what's called an initial value, okay? An initial value just narrows it down from a single solution to one unique function. So let's say we just verified that this family of functions is a general solution to that differential equation, right? Now they're saying, I want the specific function that goes through the point 0, 2. Find me that function. So essentially, solve for c and rewrite the function with the specific c that you found. All right, so here's how to solve what's called an initial value problem. All we're going to do is take 0 and plug it in for our input variable. In this case, that's t. And we're going to take 2 and plug it in for our output variable, which is y. And that should be enough information for us to solve for c, right? So I'm going to get 2 equals 1 plus c e to the 0 over 1 minus c e to the 0. What's e to the 0? 1. So this is 2 equals 1 plus c over 1 minus c. So now I'm just going to multiply 1 minus c by both sides. Right? So I get 1 minus c times 2 equals 1 plus c. We'll go ahead and distribute the 2. 2 minus 2c equals 1 plus c. Add 2 to both sides, or add 2c to both sides. 2 equals 1 plus 3c. 3c equals 1. What's c? All right. So then the specific solution that they want is the function that goes to the point 0, 2. That would be y equals 1 plus 1/3 e to the t over 1 minus 1/3 e to the t, right? And then I don't like the way this looks, so I'm going to multiply this by 3 over 3 just to get rid of the fraction. So that's y equals 3 plus e to the t over 3 minus e to the t. And I've solved what's called an initial value problem. So now we have a specific function rather than a family of functions. Does that make sense? All right, I want to go back a slide and just talk about our population model. And this is just to tell you about something that's called an equilibrium solution. Because there is in your problem set, they ask you to identify the equilibrium solutions. Is there 2 L's in equilibrium? Seems like there should be. Like that? All right, I'll Google it right after this. So an equilibrium solution happens when your rate of change equals 0. So there is no growth or decay anymore. Okay? And so in like a population model, this happens when your population stabilizes. So a population can't just continue to grow exponentially. And this is called a logistic growth model. And it takes into account what's called the carrying capacity of the environment. And so the carrying capacity is the maximum population size that will be stable for the environment, right? So like in a petri dish, if your bacteria begin to grow to the edges of the petri dish, what'll happen is then they'll grow on top of each other and start killing each other off because there's not enough room in the environment, right? On the Earth, same deal. If we begin to overpopulate the Earth, it's going to provide scarcity in environment in terms of food and water and also land mass. But there is, let's say, a perfect population size where we would be stable, and that's called the carrying capacity. And so K in this model represents the carrying capacity. Notice that once the population hits K, if P becomes K, then what happens? What's K over K? And what's 1 minus 1? This becomes 0, which means my growth rate is 0 and stable. And so at first what happens is your population will grow exponentially, but as it approaches the carrying capacity, it begins to taper off and slow down, and the growth rate approaches 0 as your population approaches the carrying capacity. But we call this an equal, oh, it is 1L. It's written right here. I'm an idiot. I was zoomed in, to be fair. I wasn't looking at the word. All right. So there are actually two equilibrium solutions for this population model. One is what we call trivial, meaning it's not interesting. And one would be the carrying capacity. If the population hits K, there is no more growth rate. Growth rate is 0. But also, if the population is 0 to begin with, guess what? There's no growth either. Unless there's like a Big Bang or something, right? Mm-hmm. So those would be considered equilibrium solutions where the population, or where your growth rate or your derivative equals 0. So values of your function that would make your derivative equal to 0. All right. And that's all I got, folks.